In this video, I'm going to show you how to derive the key results for elementary inverse functions using the chain rule. So here we've got this example: if y equals arcsine x, calculate dy dx. So we know how to differentiate sine, but not arcsine. That looks a bit challenging. And we'd rather not go back to the difference quotient because arcsine is a pretty tough function to work with. How about let's turn this into a sine problem instead of an arcsine problem, and then we can leverage the chain rule. To turn this into a sine problem, we can just apply sine to both sides of this equation, and that'll cancel out the arcsine. So we'll just have sine of y equals x. And now we can take the derivative of both sides using the chain rule. So let's just write that out explicitly. D over dx of sine y is equal to d over dx of x. Alright, so here's where the chain rule comes in. Want to differentiate sine y with respect to x? Well, why don't we differentiate with respect to y first? D over dy of sine y. And chain rule says that's all good as long as we multiply by dy dx afterwards, so the dy's cancel, and we'll just have our d over dx as we originally did. Okay, so that's what the left-hand side will turn into. And the right-hand side is easier. We can just evaluate that derivative of x is just 1. Now, revisiting the left-hand side, that's easier to differentiate now that we've applied the chain rule. So d over dy of sine y, that's just cos of y. So cos of y times dy over dx equals 1. And then we can solve for dy over dx by just dividing by cos y. So dy over dx is just 1 over cos y. We're close now, but we're not there yet. We still want our answer to consist of just x, and right now we have a y in our answer. So we want to express cos y in terms of x. So that's what we're going to do next. Next, we're going to focus on expressing cos y in terms of x. Alright, so how do we do this? Well, we know what sine y is in terms of x. Sine y is just x. So if we can get something relating sine y and cos y, then we can express sine y in terms of x, and let's just solve for cos y. So how about, do we know any identities involving sine y and cos y? How about the Pythagorean identity, sine squared of y plus cos squared y is equal to 1. Alright, so sine of y is just x, so that's going to go in for sine of y here. We'll just have x squared here. So x squared plus cos squared of y equals 1. And then to solve for cosine of y, we can just subtract off the x squared, get cos squared y equals 1 minus x squared. Then we take the square root, get cos of y equals plus or minus root 1 minus x squared. But hang on, that's two possibilities. That's one possibility, cos y equals positive root 1 minus x squared, or cos y equals negative root 1 minus x squared. So which possibility should we use in our derivative here? It really does matter which one we choose, because if we choose this one, cos y equals root 1 minus x squared, that's positive, so that'll make our derivative positive all the time. Whereas if we choose cos y equals negative root 1 minus x squared, that's negative, so that'll make our derivative negative all the time. So really we have to think, is arcsine, does that have an always positive or an always negative derivative? Is it always increasing or is it always decreasing? And to figure that out, it might be helpful to draw a graph of arcsine, just a rough sketch, so we can tell whether it's always increasing or always decreasing. In order to draw a rough sketch of arcsine, we'll need a few points for sine. So how about with sine of 0, that has to equal 0. What else do we know? Well, we know that sine of pi over 6 is equal to 1/2, and we also know that sine of pi over 2 is equal to 1. Likewise, we know that sine of negative pi over 6 is equal to negative 1/2, and sine of negative pi over 2 is equal to negative 1. And so when we draw the graph of arcsine, these become our x values here, and the inputs to the sine become the y values. Here, remember that just comes from if y equals arcsine x, then sine y equals x. So x's are the right column, y's are the arguments to the sine, and we'll just plot these points. So how about let's start plotting 0, 0, and then let's plot 1 pi over 2. So 1 will go over here, and then pi over 2 we can make right here. Pi over 2, 1 pi over 2 is right over here. Likewise, -1, negative pi over 2, so that's just pretty much the same on the other side. -1, negative pi over 2, except we're reflected over the x-axis. And then lastly, 1/2 pi over 6, so 1/2 will be right here. Pi over 6 is a little less than halfway up here, so how about right over there? And then it'll be the same idea on the other side, -1/2 negative pi over 6, so a little less than halfway up. So something like that. And we see that this function y equals arc sine x is increasing the whole way. So we got to choose the possibility for cos y that'll make this derivative always positive. That's going to be this possibility right here. Cos y is just root 1 minus x squared. So we're going to sub that in for this cos y in our derivative now, and then we'll just get dy over dx equals 1 over root 1 minus x squared. And there we go. Finally, we've got our dy dx in terms of x, and there's our final result. Alright, so we've done arc sine, but how about if y equals arc cosine of x, calculate dy dx? Well, this is really similar. Again, we know how to differentiate cosine, but arc cosine is a bit of a different beast that's a lot tougher. So we want to convert this into an equation which is easier. How about we just take cosine of both sides? So cosine of y equals x. Now this should look really familiar from before, so let's blow through it a lot faster. So we're just going to implicitly differentiate d over dx of cos y equals d over dx of x. D over dx of cos y is just d over dy of cos y, which is negative sine y, then times our dy over dx. And then on the right hand side, d over dx of x is just 1. And then we can solve for dy dx, get dy dx is just negative 1 over sine y. Again, we want to express sine y in terms of x. We want our answer to be in terms of x entirely. So what do? Well, we use the Pythagorean identity, sine squared y plus cos squared y equals 1, and then we'll just take this cos y equals x and we'll sub that in for cos squared y here, and we'll get sine squared y plus x squared equals 1. Solve for sine y, get sine squared y equals 1 minus x squared, so sine of y equals plus or minus root 1 minus x squared. So that leaves us with two possibilities, either sine y equals positive root 1 minus x squared, or sine y equals negative root 1 minus x squared. Again, these two possibilities cause the derivative to take on two different signs. If it's sine y equals positive root 1 minus x squared, then the derivative will be negative, because that negative in front doesn't cancel out with anything. Whereas if sine y equals negative root, then the negative in the derivative will cancel out with that negative there, which will go in the denominator, and then it'll be positive. So really we just need to tell, is our cosine increasing or decreasing? And we can draw a rough sketch of our cosine. Let's just plot a couple points here. So cos of pi over 2 is just 0, so that gives us a point 0 pi over 2. Cos of 0 is just 1, so that gives us a point 1, 0. Cos of pi is negative 1, so that gives us a point negative 1 pi, and pi will be up here, say, so it'll be right about over here. And from here we can draw a rough sketch of the graph. It looks something like this. That's y equals arc cos of x. And based on this graph, we can tell that arc cosine is decreasing the whole way, so the derivative needs to be negative. So we want to choose sine y as positive so that it won't cancel out that negative in front. So subbing this value for sine y in, sine y is positive root 1 minus x squared, we find that dy dx equals negative 1 over root 1 minus x squared. There we go. There is our derivative. Before we move on, one way to remember this is to notice that the derivative of arc cosine is just negative of the derivative of arc sine. So really you just need to remember this 1 over root 1 minus x squared part. And then if you're taking the derivative of arc sine, then you keep that positive. If you're taking the derivative of arc cosine, you do tack a negative on there. Alright, here's a last example. Y equals arctangent of 2x, and we want to calculate the derivative. So this is pretty similar to the arc sine and arc cosine problems. Now we just have arctangent, but we've also got a 2 on the x there, which will make things a little bit different. But let's go ahead and take the same approach. So we'll just cancel out the arctangent by applying tangent to both sides. Tangent of y is equal to 2x. Then let's differentiate both sides. D over dx of tan y is equal to d over dx of 2x. D over dx of tangent y, using the chain rule, we can express that as d over dy of tangent y, which is just secant squared y, as long as we multiply it by dy dx afterwards. And then on the right hand side, d over dx of 2x, well, that's just 2. So we solve for dy over dx, and that's just equal to 2 over secant squared y. Again, we want to express secant squared y in terms of x, so why don't we use a trig identity here? Let's start off with what we were using before, sine squared y plus cos squared y equals 1. And we know what tan y is, so why don't we rearrange this equation to get to tangent. So we'll just divide everything by cosine. Sine over cosine is just tangent. We'll divide everything by cosine squared y over cosine squared y over cosine squared y. Then sine squared y over cos squared y, that's just tan squared y. And then cos squared over cos squared, just 1. And then 1 over cos squared is just secant squared. Alright, so now we've got a nice equation that we can use to plug in tangent y and get secant y in terms of x. So tangent y, that's 2x, so we're going to plug that in over here. So this becomes 2x squared plus 1 equals secant squared y. So just square that and you get 4x squared plus 1 equals secant squared y. Great, so now we can just sub that right in for secant squared of y in our dy dx. So dy dx is just 2 over 4x squared plus 1. Now this is a totally fine way to leave it, but you'll usually see dy dx of tangent, you'll see it expressed with 1 coming first in the denominator. So you'll see dy dx equals 2 over 1 plus 4x squared. The only reason for that is that it's easier to remember because the derivatives of arc sine and arc cosine, they have 1 minus x squared inside of a root in the denominator. So if you think of tangent is just 1 plus something x squared, then it's kind of like they all take somewhat of the same format. But here we go. Here's our derivative. Dy over dx is just 2 over 1 plus 4x squared. Great, now we know how to differentiate inverse trig functions. And in the future, we'll gain more practice remembering and working with these rules to differentiate more complicated inverse trig expressions.